Ever notice how a radio station comes in loud and clear at one dial position, but fades when you drift away? Circuits can do the same thing. At one special frequency, the response spikes. In this video, we're exploring LCR resonance and using visuals to understand resonant frequency, the frequency that gives the maximum current for a fixed source voltage. For our purposes, resonance means the maximum current for a fixed input voltage in a series RLC circuit. So resonance is the point where the current becomes as large as it can. To see why this happens, we need to look at how frequency affects current. The key twist in AC circuits is that you can change the current without changing the parts, just by changing the frequency of the source voltage. So the big question is, which frequency gives the maximum current? The peak current equals the peak voltage divided by the impedance magnitude. If the voltage stays the same, the current gets biggest when the impedance magnitude gets smallest. In a series RLC circuit, impedance depends on resistance and on the difference between inductive and capacitive effects. Resistance doesn't change with frequency, but the reactive part does. So we hunt for the frequency that makes that reactive difference as small as possible. Capacitive reactance is large at low frequency and shrinks as frequency rises. Inductive reactance is small at low frequency and grows as frequency rises. So as you sweep frequency, one goes down while the other goes up. Because the reactive term is squared, the smallest it can ever be is 0. That happens when the two reactances match. Inductive reactance equals capacitive reactance. That's the resonance condition. When those two reactances match, the circuit is at resonance. Solving for that condition gives the angular resonant frequency. Omega naught equals 1 over the square root of L times C. Converting to ordinary frequency gives F naught equals 1 over 2 pi times the square root of L times C. Let's see what that looks like with actual numbers. Let's do one example. Suppose L is 0.2 Henry and C is 50 microfarads. Plugging into the formula gives a resonant frequency of about 50 Hz. That means the current peaks around 50 Hz for this circuit. But resonance is often misunderstood. Here's a common misconception. People think resonance means infinite current, but in a real circuit, resistance is still there. So at resonance, the impedance is essentially R. That means the peak current is limited to about V peak over R, maximum current, not unlimited current. So far, we've covered that current peaks when impedance is smallest. That happens when inductive and capacitive reactance match, and the resonant frequency depends on L and C. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Now let's build a picture of what's happening. At very low frequency, the capacitor's opposition is big, so current stays small. At very high frequency, the inductor's opposition is big, so current is also small. In the middle, at resonance, they balance, and current becomes largest. Here's a powerful takeaway. If you increase capacitance, the resonant frequency goes down. If you increase inductance, the resonant frequency also goes down. For example, doubling C makes F naught smaller by a factor of square root of 2. But the height of that peak depends on another factor, resistance, meaning the circuit's effective loss controls how sharp the resonance feels. With low loss, the peak is tall and narrow, very selective. With higher loss, the peak is shorter and spread out, so the circuit is less picky about frequency. Resonance also affects how voltage and current line up in time. At resonance, the inductive and capacitive effects cancel, so the current's impedance is essentially just R. That means the current and the source voltage are in phase. Their peaks happen at the same time. To recap, maximum current happens when impedance is minimum. That minimum occurs when inductive and capacitive reactance match, and the resonant frequency is 1 over 2 pi times the square root of L times C. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.